Jai Hind everyone. So in today's lecture, we will be learning about disk scheduling algorithm. In the previous lecture, we have learned first come first serve algorithm. Now in this lecture, we will be seeing the various disk scheduling algorithms after FCFS. So in the last lecture, we have studied all these things, and in first come first serve algorithm, we have seen that we are accessing all the values of the disk, all the values of the queue from the starting to the ending point, depending upon where is my header, and I am actually I'm accessing all these value in a forward fashion. So whichever is the first value, I am accessing that, and again I am following this loop. So in first come first serve algorithm, actually it is handling all your input output request sequentially. So the word sequentially should matter here, because we are actually doing in a very sequential form. So it is very fair process. It is not actually giving a priority to one process or giving you can say priority to another process, like your waiting time is less, or your priority is higher. No, it is very fair to all the processes. But definitely the approach is random scheduling in performance if there are many processes requests. So this is like your performance will not be efficient performance into this particular algorithm, because it is randomly scheduled. So it is like, okay, you are at this particular level, now you are having a request at this particular level. So in that case, your disk head will move frequently. It will not optimally used. So that's why your performance will be degraded if your scheduling requests are very random. Okay, and it suffers from global zigzag effect. Again, as I told you so, because it is what? It is doing a zigzag pattern. If you are having request at 124, then you are having request at 14, then you are having request at 183. So it is like your read write head will be moving in a zigzag fashion. So it is also not a efficient way to access all the requests. So now what? So there are other algorithms for it. So the second algorithm here that we're going to study is shortest seek time first. So what happened into it is, as per the name, whichever is the seek time which is being given here is the shortest from our read and write head, we will be accessing that particular value first. So again, my head starts at 53. Now I am at 53, this particular level. Okay, now the request comes at which is 98. But what I have to see, which is the smallest request first. So, and which is obviously closer to this particular read write value, because we are accessing the values which are having less seek time or the short seek time. And the seek time, I have already told you that if my header is at particular one section and you are moving my header to another section, so this particular movement is your seek time. Okay, moving from one point to the another point is known as seek time. So if I am at 53, I have to see which would be the nearer point that I need to access. 98 could be, 183 no, 37 yes, it could be possible, 122, 14, 124, 65 and 67. So you can see, if I am at 53, you have to subtract 37, see the difference, subtract 65, see the difference, which is the lesser one. So when I am subtracting 65 and 53, so this is the least distance that I am having. So I'll go to the 65 first. Then again from 65, I am again accessing the value which is lesser. So that is 67. Now after 67, which is the lesser one, that is the 37, and then 14. So after 14, what I am going to see is, which is again the lesser one, that is 98, then 122, then 124, and at last it is 183. So in this particular algorithm, you are going to see that every time you are actually finding out which is the lesser point that needs to be accessed, so that that particular point is tracked down first, and after that you are moving to the higher point. So in this way, there are some plus points and minus points for this. This is like you are selecting the request with the minimum seek time from the current head position. Definitely, this is what we have done. Also called shortest seek distance first. So this algorithm is also known as seek distance first, shortest seek distance first. So it is easier to commute the distances. So if you are commuting from one point to the another and you know which is the shorter one, then this particular algorithm will help you out more. So it is biased in favor of the middle cylinders request. So whenever you are having the request which is into the middle part of the area, like in this particular section, I'll show you. In this section, whenever you are having track numbers which are inside this area, spindle, okay, that is very much easier for your you can say shortest seek time first algorithm, because in that particular section you are actually accessing those requests which are very nearer to each another. So if I am having from 0 to 199, so in that case, if my header is at, consider it is at 40, so it is beneficial or efficient for me to move between 40 to somewhat between 80, so that my process or my head will be actually accessing only these points. It would not be like from 40 I am going to 199, then I am going to 0, and then I am going to some other value. So you are not actually you are not creating a zigzag pattern here. So you are actually accessing all these values in a very linear form. Okay, and the last one is shortest seek time for scheduling is a form of SJF scheduling. So this is again, when we have studied about various scheduling algorithm, then we have learned about SJF, shortest job first. So this is also a form of SJF algorithm that may cause starvation of the some request. Definitely it would happen whenever you are having a kind of request which are into the middle part. Consider this is the middle part. So whenever you are having requests which are inside these values, this particular request like 183 or 199 would be in the position to starve, because every time your header will be going for the shortest distance, and every time it is actually jumping from one to the another only when it is having a shorter way. So at the larger values, it is a kind of the situation when starvation occurs. Now the other algorithm that needs to learn here is elevator algorithm. So algorithm based on the common elevator principle. So there are 4 combinations of our elevator algorithm, that is scan, C scan, look and C look. So what is the combination here? It is go until. So in this way you are going until the last cylinder. So this is like when you are traveling from one point and you are accessing those points which are coming into this way, but what is the main motive is you have to access the last point irrespective of it is being required or not required. So I need to go to 199. Suppose this 199 is my last request, so I need not last request, this is the last point. So every time my header, whenever it is going into a linear value from this particular side, or you can say consider this is my left side and this is my right side. Okay, so every time when my header is moving from up from a point to left side or from a point to right side, so every time if I am going from one point to the right side or left side, I am going to the extreme value, that is 199. So go until the last cylinder, that is scan and C scan. Go until the last request. So what would be your last request? It could be like in this particular question, I am having 183 is my last request. So every time whenever I am moving, I need to go to this particular section, that is 183. Direction, in which direction? So service both directions. So scan and look, it will be servicing into both direction, it will go into both directions. So service only one direction. So C scan and C look will be servicing you only in one direction. So let's see what happens into it. So this is the example of scan algorithm. Again, we are having Q with us. Our header is at 53, and this C. Scan will be accessing the both direction, and it will go until the last cylinder. So keep that in mind. So my header is at 53. I'm starting from 53. My next value is 98. But shall I go to 98? No, I'll again find out which direction I need to move on. So select any direction of your choice. It could be left, it could be right. So I'm starting from the left here. You can start from the right also. It is totally up to you. So my read write header is at 53. It will start from left, and whichever the number is being required are poking onto your left side, that will be accessed first. So on the left side, I am having 37 accessed. Left side, I am having 14 accessed. And what? I will go to the end point also. This is what has been written here. Go until the last cylinder. In which direction you have moved, you have to go to the last cylinder. So you need to go at 0, and after that 0, you need to switch your direction because this is the last point, and then you will going to the another direction, that is right direction, and on the right side, whichever the value you need to track, that needs to be tracked first. So 65, 67, 98, 122, 124 and 183. Now you don't need to go to 199. So this is only a ones that is being used here, that either to the left side or to the right side, whichever the direction you have chosen first, okay, whichever the direction you have chosen, you have to go at the end point, and then you have to revert to the next direction. So this is the scan. Okay, so the disk arm starts at one end of the disk and moves towards the other end, servicing request until it gets to the other end of the disk. So where the head movement is reversed and service continues. So this is what we have did in our last example. It moves in both directions until both ends. Okay, tends to stay more at the ends, so more fair to the extreme value. Whenever the extreme request has been generated, it is fairer as compared to your FCFS or SJF. Now for the look, so what happens in the look is, the disk arm starts at the first input output request on the disk and moves toward the last input output request on the other end. So again, this is also similar as we have learned here in look. You have to go until the last request. So whatever your last request, like this is your 183 is your last request, so you need to move to the last request first. So this is like disk arm starts at one end of the disk and moves toward the other end, servicing request until it gets to the other end of the disk where the head movement is reversed and servicing continues. And in look, the disk arm starts at the first input output request on the disk and moves toward the last input output request. So if I'm starting from, it could be like, suppose on this scale you are having 0, you are having 199, you are at 53, you need to travel from one direction to the another. So at 53, you will be starting to the right direction, because first of all you need to access the last request. So you will going in this direction, and whatever the request falling into this particular direction, that is being accessed first. Okay, so this is written here like the disk arm start at the first input output request on the disk and moves towards the last input output request on the other end, service request until it gets to the other extreme input output request on the disk. Okay, so you will be moving into this direction and this until you are having the last request, that is on 183, that is being accessed, and then your direction will be changed only. Okay, it moves in both direction until both last input output request more inclined to serve the middle cylinder request. So this is as similar as your scan algorithm. Only difference is that you have to access the last value, but in look you have to access the last request first. So this is like either starting from the left or starting from the right. you need to see which would be your last request. You need to access your last request first, and then you have to calculate your other values that needs to be tracked down. Okay, now in C-scan, so again in this particular value C-scan is service only in one direction only, and it will also going to your value which is being associated as your last endpoint. So in C-scan, my last endpoint is 199. So I'll go from one point to the another and will head towards 199 only, and then I'll change my direction. Not the direction, but yes, the path, and the direction will continue in a similar way. So this is like if I am at 53, I need to go to 199. This is the last value. So this is the right direction. So I am starting from my point 53 and I am choosing my direction right. You can choose your direction left, but for that what happens is you need to, you need to go from this value to the 0, and then you need to start here. But you need to remember that in C-scan, what happens is that you have to track the last value of the cylinder, and this is the first value of the cylinder. So in this case, left option is not available. Okay, so in any case you need to start from your value and go in the right direction only. So from 53, what has been tracked? 65, 67, 98, 122, 124, 183 and 199, because this is the last value, and C-scan goes to the last cylinder value. Then it will go to the first point, and then again it will change its direction. So it is right, again it will be right, and then 14 is being accessed and 37 is being accessed. So this is your C-scan. So the head moves from one end of the disk to the other, servicing request as it goes. When it reaches the other end, however, it immediately returns to the beginning of the disk. So this is what? This is going to the last end, but it will return to the beginning of the disk, and then again it will start tracking down your value. Okay, without servicing any request on the return tab. This needs to be make sure that you don't need to, you cannot actually access those requests when your disk header is moving from extreme endpoint to the starting point. Then after that your direction will change, and then only you will be going to access those points. It treats the cylinder as the circular list, wraps around from the last cylinder to the first one. So it is actually using your cylinder in a kind of a circular form. It is going from one end to the another end, completing those parameters which are the starting and the ending value. Okay, it provides a more uniform wait time than scan. Definitely, it treats all the cylinders in the same manner. So these are some of the plus points of C-scan. Now this is C-look. So again, go to this particular diagram and see. C-look is obviously servicing in one direction only and go until the last request. So let's take an example. So in C-look, my header is at 53 and one direction I can only serve. So I will go in the right way only. Then 65, 67, 98, 122, 124, 183. Now, it will not go to the extreme part of the cylinder. It will only go to the last request. So the last request is 183. So it will stop in 183. It will not go to 199, and at 183 it will change its path and revert to what? The access point. It will not again go to 0. It will not covering these values 0 or 199, whatever the starting or the ending value, it will not cover. It will only cover the values which are being tracked down in this queue. So after 183, the next value will be tracked down, which is in another direction, that is 14. So it will track 14, and after that 37. So C-look works like C-scan. Okay, and then arm only goes as far as the last request in each direction. So your arm is going as far as your last request is being made. So last request was at 183. So your arm is going to the last request, and in between this particular request, if there are another tracks that needs to be tracked down, then these particular tracks is being tracked. Okay, so as the last request in each direction, the reverse direction immediately. So it will be it will be reversing the direction immediately when only it is accessing your last request. Circular version are more fair but pay with a larger seek time. Why larger seek time? Because whenever you are calculating the total seek time here, so here you can see you are starting from 53, you are going to 183, and then again you are switching to 14. So this is like this particular, this particular seek time is waste. So definitely it will going to give you the larger seek time as compared to another algorithm. Scan versions have a larger total seek time than the corresponding look version. So all these scan version like C scan or scan, they'll give you the larger seek time as compared to look or C look. So this is the these are the various you can say algorithm that has been implemented under the disk scheduling, and these algorithms will give you a kind of a scenario in which your data is being accessed, and this is the first come first serve, then shortest seek time, then these four algorithms come under your elevator algorithms. Okay, scan, look, C scan and C look. Thank you everyone.